All right, so for the last talk of the day, we have Sesh, who's going to tell us about the long path to monotonicity testers. I don't think I need to introduce Sesh. If you don't know who he is, just look at any of the programs on sublinear algorithms over the past N years, and there's going to be a biography there. But yeah, so thank you.
Thanks a lot, Timo. And well, thanks for making it to the last talk. I know everyone's tired. I also wanted to thank the organizers for WoLA for like the wonderful workshop so far, the program, and especially Clement for keeping things alive while so many things are happening. So thank you very much. So yeah, so there's a minor pun here, the long path to root T monotonicity testers, and hopefully you'll see it later on. I always like to begin by expressing my indebtedness to my teachers, Manindra Agarwal, Bernard Chazelle, Mike Sachs, Tamara Kolda, and Ali Pinar. Also, this is joint work with Hadley Black, who should be here. There he is. And my longtime comrade in arms, Deeparnam Chakrabarti. And so let's go ahead and begin. So the main sort of beast or object of study is Boolean functions on the hypergrid. So by now, I think you've seen enough that hopefully much of this should be clear. But the hypergrid is essentially the set n to the d. So think of it as it includes the line if d is equal to 1, the grid. There's this word. Does anyone know what that word tesseract means?
Yeah, it's in the Marvel movies.
But it actually has a very specific geometric meaning. Okay, so you'll learn something out of this talk if you learn nothing else. Apparently, the 4-dimensional cube is called a tesseract. I don't know. Yeah, so they actually have a word for it. So when n is equal to 2, of course, this is the Boolean hypercube, which we know and love. And this is endowed with a natural partial order where element x is less than y if all the coordinates of x are less than all, corresponding all the coordinates of y. And what is a monotone function? So if x is less than y, then f of x is less than equal to f of y. That's what a monotone function is. Of course, for this definition, we don't need the function to be Boolean. This can hold for anything. But since we're studying Boolean functions, we can equivalently think of this function as the indicator of some set, or its indicator of some subset of the hypergrid. And so this is sort of my cartoon picture for a hypergrid. I always put the all zeros point below, the all n-1 point above, and this is like a monotone function there. So what is the distance to monotonicity? So I can read through this, but think of it as you're given some function that is not necessarily monotone. You want to make it monotone. And the question is, what is the minimum amount of change that needs to happen? So the change can happen either by deleting some part of the set and by adding something to the set. So basically switching a 1 to a 0 or 0 to a 1. And that total amount of change is the distance to monotonicity expressed as a fraction. So formally, it's the minimum number of changes that you need to make the set or the function monotone divided by n to the d. So that is the distance to monotonicity epsilon f. It's in 0, 1, amen to that. And equivalently, you can also say that it's the distance, it's the minimum distance to a monotone function, right? So you're minimizing over all monotone g of the L0, the Hamming distance between f and g. So that's the distance to monotonicity. And monotone functions, as we've seen throughout this workshop and in general, are very interesting objects of study. And so it's natural to ask, can you learn a monotone function with samples? And since Bshruti and Tamon, and there's also like recent work by Lange and Vasilian, that to learn a monotone function, you need exponential and square root d queries, where d again is the dimension. And so one of the interesting, this is where like the birth of property testing came in, is that are there certain properties where you can test faster than you can learn? And so specifically given some epsilon, which is the proximity parameter, and query access to a function, we want to distinguish a monotone function from something that is far from monotone. And this is the sort of standard property testing setting. And by and large, I'll focus on one-sided testers, which means that when the function is monotone, it always has to accept, which, conversely, what it means is if you're given something that is far from monotone, you have to discover a violation to monotonicity with high probability, and again, with some constant probability. So, and I'm going to focus on non-adaptive testers here, which means all the queries are made in advance. So again, the cartoon picture for that is you have some function that is far from monotone. There's some sampling procedure that's going to sample a bunch of points on the hypergrid. And it's trying to find this violation to monotonicity. So it's an X that's inside the set, a Y that is outside the set, such that X is less than Y in the partial order. Right? This is a violation to monotonicity. So when I say violation, that's what I mean. Okay? So the aim of a property tester is you're given a function that's far from monotone. How fast can you find one of these? Right? And that's the problem. And this problem has a very rich and storied history. So starting from the papers of Goldreich, Goldwasser, Lehman, Ron, and Samorodnitsky, and then there's Sofia Raskolnikova's master's thesis, as well as Doris, Goldreich, Lehman, Raskolnikova, Ron, and Samorodnitsky papers around the same time, which were studying this problem of what is the non-adaptive complexity of monotonicity testing. So you're given this function, hypergrid domain Boolean range. Let's just fix that. And how many queries are needed to non-adaptively test monotonicity? Basically find a violation if it's far from monotone. And it's a rich history of like more than 20 papers and sort of 2 decades of history on this problem. And this to me, I mean, I wish I could, this is amazing that they could sort of come up with this problem, which at some point is so easy to describe, right? I described it to you in 2 slides. And yet, you study it and more and more and more keeps coming out. So it's really incredible that this one problem could lead to so much interesting work. And I hope to demonstrate more like, various deep theorems in mathematics that have sort of emerged from this study. I'm going to start with sort of a classic result from these papers. So I'm just going to refer to them now as GGLRS and DGLRRS. This is the edge tester of the hypercube. So the way it works is, so you've got your hypercube, and you have this sort of unknown set that you're querying, or this unknown function. So we're going to sample an edge of the hypercube uniformly at random. So you sample 2 neighboring points on the hypercube, which is like you sample a random point and flip a bit. So we're fixed, like just doing a hypercube right now. And you query both these points and you reject if it's a violation. Right? It's a pretty simple test, right? A simple local test. And I will explain this more as we go along, but then the classic theorem of GGLRS is that the probability of finding a violation is at least epsilon f over d, where epsilon f was the distance to monotonicity. And again, like you can just think of that as a constant for now. So the probability of finding a violation is like 1 over d. And so, just taking the inverse of that, you need d over epsilon samples to detect a violation, with constant probability, and you can boost that. Right? So is this clear? And it's likely that this theorem is familiar to many of you. Maybe if you've taken a course in property testing, like this is one of those nice classic results that's often taught. And for the hypergrids, there is a d log square epsilon or divided by epsilon monotonicity tester. It's a little more complicated. So instead of an edge, it chooses a random line. And then there's a little bit more work that needs to be done there. But essentially think of it as, you're picking this one-dimensional object, and then you're checking monotonicity on that one-dimensional object. And we've sort of seen that flavor in, I guess, ST's talk on like, testing, low-degree polynomials. Like you choose like some one-dimensional object and you check it over there, which is this natural test. And this is such a natural test that you can ask, can you do any better than this? Right? Because it seems like a nice canonical test. And so so again, like just to give you the sense of the year, so this is, about 99, 2000 when this work came out. In 2012, Blaise, Brody, and Matleff, in a very beautiful argument with communication complexity, showed that there's actually an omega d lower bound for this problem when the range is real. So not the Boolean case, but when the range is real. And then subsequently, in a couple papers with Deeparnam Chakrabarty, what we showed is that if you're doing the hypergrid domain arbitrary range, so range could be real, then the complexity, we can sort of nail it down. It's actually d log n by epsilon, basically. Right? So what is d log n by epsilon? It's like log of the domain size. Right? That's one way of looking at it. And this seemed like, okay, this is the end of the story, right? It's a non-adaptive one-sided upper bound. The lower bound is an adaptive two-sided lower bound. And the optimal tester, when you look at these results for the hypercube, is the edge tester. The optimal tester for hypergrid is a little more complicated, but again, it's about looking at a one-dimensional structure and then looking at the function restricted to that, sort of. Right? So it seems like, okay, this is it. And the question really is, does the fact that the function of Boolean range make the problem any easier? Because if you think about the tester doesn't really seem to care about the range. All it's doing is like it's starting at a point, doing some process, finding another point, excuse me, and just comparing values. But the only lower bound that was known was by Fisher, Lehman, Newman, Raskolnikov, and Rubenfeld, which had many results on monotonicity. Specifically, what they showed is there's an omega root t one-sided lower bound. Again, this is, sorry, non-adaptive. Non-adaptive, one-sided lower bound. And so, you know, there was a feeling that the truth is probably the D. And, you know, just to give you a little bit more context, often in property testing, there's like this very simple canonical tester that most of us can just guess. And often it is optimal. Of course, the hard work goes into proving that that simple canonical tester is optimal. And so it was initially a bit of a surprise that we could go below D. So the first result in this was with the Parnab Chakrabarti, we got a D to the 7/8 query tester. And very soon after that, Chen, Cervedio, and Tan essentially tightened our analysis and got D to the 5/6. And at that point, it was clear that from whatever understanding we got, D to the 5/6 was the best we can hope for. And then a few years later, there was this breakthrough by Kote-Minzer and Safra, which gave a square root T query tester. And I'll explain how these results come about. It's essentially the same tester in all cases. It's just the analysis that was being tightened. And the subsequent works of Chen, Day, Cervedio, and Tan, Chen, Weingarten, and Chia showed that there's an omega square root T two-sided non-adaptive lower bound. So one-sided adaptive, non-adaptive lower bound, one-sided non-adaptive upper bound, two-sided non-adaptive lower bound. Yes?
This one, the edge tester is a POT, a proximity oblivious tester, right?
Correct.
Are those as well?
Yes, they are.
Oh, okay. So it's not that you can prove a lower bound against POTs that...
No. No, and I'll show you the tester. So it's again just querying pairs, and it's just how many times you need to do it. Yeah. So the root D turns out to be the right answer, and just to give you a sense of like the complexities of these papers. So the edge tester bound, again, as I said, like as I mentioned yesterday, is about 2 pages of a proof. This is maybe about 7, 8. This is about 30 pages. And this is a very challenging paper to read because it turns out that to actually get down to root T, they had to discover something quite new about the hypercube. And that's what much of this talk is going to be about. I can basically spend the entire lecture talking about them, which is what I'll probably do anyway. And this led to what's called the theory of directed isoperimetric theorems, which is what I will talk about. But seemingly, this was very hypercube specific. If you looked at their proofs and you looked at even the earlier stuff, it felt like it was using the hypercube. Question is, can this generalize, beyond the hypercube? And so the story since then recently has been we can actually get to root T even for hypergrids. So again, just going back to what happens for hypergrids, which are n is greater than n is arbitrary. So D, GG, LRS give a D log square monotonicity tester. Berman, Raskolnikov, and Yaroslavtsev shaved off a log factor. And then in joint work with Hadley Black and Deeparnab, we were able to get a D to the 5/6 query, trying to follow sort of the same route. And then in 2023, this is just like a couple of years ago, Braverman, Cote, Kindler, and Minzer, and us independently, we gave a poly-n square root T tester. So this is sort of, you got the dependence on D, but the dependence on n was polynomial. Now, the reason why this was interesting, it was not clear that for any n greater than 2, whether you can actually get that root T bound. And most recently, we have like essentially a root T tester. There's some annoying little o of 1 in the exponent. And what is kind of curious is all of these results actually have different testers. Although maybe they could all be the same, but they're like various differences in the testers. In the hypercube case, it's all basically the same. Okay. And so much of this is the story of the talk. And a lot of my focus will be basically in trying to explain the KMS result, which I think is like, this is this gem that I would like to show. But before I do that, I want to tell you why hypergrids. So of course, it's a natural generalization. But something that's really nice about the hypergrids is essentially, suppose you want to do property testing on hypercubes under some other product distribution. So like each coordinate is chosen with, with p it's 0 and probability 1 minus p it's 1. So you can automatically translate that into a hypergrid problem. So what this means is, if you take uniform distributions on the hypercube, that's just uniform distributions, sure, that's the standard setting. But if you take non-uniform product distributions, you can convert that to a uniform distribution over a hypergrid, which you can imagine just by doing some sort of precision games. So what's nice is that when you have results on the uniform distribution for hypergrids, you actually have you have distributions for any product distribution on the hypergrid, sort of automatically. Yes?
Need it could be like the actual continuous cube or something.
Very well planted question. I told him to ask me that. No, I'm kidding. But yes, exactly. So the fact that you can get this independence of n means that you can even set n to be infinity. So your domain is r to the d. And now you're doing monotonicity testing for sort of measurable functions, like measurable sets, because you need to have some notion of measure so that you can actually define what symmetric difference and things are. And so that's why the hypergrids are really nice, because you sort of get these product distributions for free just by doing uniform, which when you start thinking about it is a bit tricky, because when you think about the hypercube, often you use facts like, oh, most of the mass is in the middle layers, so it's n over 2 plus minus 1 plus minus root n, and all the action is happening there. When you're in a non-uniform distribution, then you sort of have to shift that. It's not, some of those facts don't hold, and you wonder like, how do you generalize? But for hypergrids, somehow that problem goes away. Okay, so any questions? Yes.
Yeah, similar question, like the fact that doesn't depend on n. If you set d to constant, like d equals 1, does it mean that with constant values you can?
Yeah, because if you think about like d is equal to 1, that's just the line. So what is sort of like a measurable function? It's just some union of intervals. And so if that is far from monotone, then usually there's like a large enough interval of zeros that is after some large enough interval of 1. So if you sample enough, you'll just hit that. Because, so yeah, yeah. I don't know if that answers your question. Okay. Question. Why did the baby grid not get any sugar? Because it would become a hypergrid. Sorry. Directed isoperimetry. So this is a question of why surfaces, volumes, and why little of these possible. Does anyone can anyone guess what that picture is? Why did I put that up there? So, okay, so this is, I Googled, this is the picture of Queen Dido of Carthage. And apparently the first time that the isoperimetric problem was described, historically or mythically, is in the birth of Carthage. And that was the queen. And apparently she solved the problem to get like the city or something. And you can ask me more about it later. And that's why I draw the circle, because this is like the classic isoperimetric problem says, for all shapes of a given area, how do you minimize the surface, right? What is the minimum surface? And it's the circle in 2 dimensions that solves the problem, right? And in 3 dimensions, it's a sphere, which is exactly why like droplets of water are spherical, right? Because that minimizes energy. So people have been trying to study this issue of like, if you fix the volume, then what is the minimum surface area? And we're going to see that phenomenon is actually going to play into all these monotonicity testers, which is quite fascinating. Okay, so how? So let's go back to the edge tester. So remember, we sampled an edge of the hypercube, we queried the endpoints, and we checked the values. And the theorem was that the probability of finding a violation is at least epsilon f divided by d, where epsilon f was the distance to monotonicity. I want to give a geometric interpretation of this. So let me draw it in the following way. So this is my hypercube, remember, directed from bottom to top. And this is my function S, or the set of ones. And this is far from monotone. So what this theorem says, the GGLRS theorem says, is the number of violated hypercube edges is omega of epsilon f times 2 to the d. So what are those edges? Those are these edges, right? Starting from a 1 going into a 0. So that's the number of violated edges. And so let me just write this definition down. And it's deliberately written in a somewhat provocative way. I'm going to call it inf plus is the number of edges that go from the set to the complement, but with direction, divided by 2 to the d, just normalizing. So if you've seen Boolean functions, what is inf? Influence, right? So this seems like some kind of directed influence, like just this bound. You can interpret it as some kind of directed influence. And what they're saying is that for any f, the directed influence is omega epsilon f. The directed influence is at least the distance to monotonicity. Now, okay, so let me now connect it to maybe something that we're more familiar with. Let's just ignore direction. Let's look at the undirected case. Right, so you just have some subset of the hypercube, and you look at the edges that go from the set and leave the set. That's the boundary, right? That's the influential edges. So the classic definition of influence of a function, so again, S is the subset of ones and F is the function. I'm kind of abusing notation. So it's the number of edges that go from the set to the complement divided by 2 to the d. And this is the classic notion of the influence of a Boolean function. And the Poincare inequality, or the edge expansion bound, or the influence bound, whichever way you call it, basically says that the influence of a function is omega of the variance of the function. So variance you can think of as like the number of ones divided by 2 to the d times the number of zeros divided by 2 to the d. But if this bothers you, just think of this as some subset that's half of the whole thing, right? Because if almost everything is 1, then you're not going to have much of a boundary. So you need this sort of normalization factor, right? And so this is just the variance of the function. Again, if it bothers you, or if you want to have, you want to strip this away and just get clearer intuition, I like to think of this as some constant fraction subset of the hypercube. So what this says is take any constant subset fraction of the hypercube, the influence is omega 1, right? Which is like an edge expansion bound, which is equivalent to the edge expansion bound of the hypercube. Yeah, questions? And this, again, like, you can prove by induction, right? If you set up the right inductive hypothesis, proving this is not very difficult. Now, the reason this is sort of an isoperimetric theorem is you can think of this influence F as like a surface area. And this variance is maybe some kind of volume. It's like some kind of, if this was less than half of the set, then essentially it's just the number of ones divided by 2 to the d. Right? So it's basically some measure of, it's just like a normalized size, which is volume. And this influence F is like what's happening at the boundary. Yeah? Questions? Okay. So this is now quite fascinating that the GGLRS bound looks like a directed Poincare statement. Right? So what I'm saying is the undirected hypercube, the Poincare inequality says influence is omega of variance. And the GGLRS bound says this influence plus, which is this directed influence, which is going upwards from a set, is omega of epsilon f. So it's like this is some kind of a directed expansion or directed surface area. And epsilon f is like a directed volume, somewhat strange. It's a very different way of thinking about what epsilon f is. Now, what's surprising is that this bound was known for a long time, but it's only after 15 years of that bound that we actually started seeing this parallel. And once this parallel opens up, you start wondering, wait, what other theorems can I prove here that are isoperimetric? And then can I transfer them back to this world over here? Right? And that's basically the story of how the D bound was beaten and improved upon. Okay? And so, so questions? Okay. So let's talk a little bit about more about the Poincare inequality, and just to see that this bound is actually tight. And there's a fairly simple example showing that it's tight. Does anyone, I already flashed the slide in front of you, but you know, like when is the edge expansion bound tight? Assume that this is half of the entire body, and just take the hypercube. Take the hypercube. What is the function that minimizes the influence? Assuming it's about half. Yeah? Huh? Yeah, the dictator. Dictator, half space, right? So let's take the dictator. And I'm just going to consider the anti-monotone version because I'm thinking of distance to monotonicity. In this case, actually, it's all the same. So the distance of this function, so the directed Poincare are both tight by this example. Take the dictator function. The distance is half, right? Because you sort of have to change all of these values to 0 or all of these to 1. The number of violated edges is 2 to the d minus 1, like all the edges that are crossing this dimension. And the total number of edges is d times 2 to the d minus 1. And so this is showing that Poincare is tight. It's also showing that the edge tester needs omega d queries to catch a violation, right? Okay. So we know that Poincare is tight. So now so I'm sort of switching back to thinking about monotonicity testing. One could even start with this instance and say, what is it that we could do over here to actually beat this d bound? That makes sense? So immediately it's like we need a new tester. So the canonical tester that we thought about is not going to work. And so, okay, so here's, let me sort of explain what I'm going to do. So I'm going to show you a tester, which is going to beat this d bound for this example. Then I'm going to try to connect it back to directed isoperimetries and then sort of complete the story. Okay, so what you could do is you could sample some x. You could do a long walk, random walk, but upwards, right? Start at a point, keep flipping bits, but flip zeros to ones and query y and then, check, right? So make sure, like, what is the probability you're going to start from here and end up over there? Question is, how long should we walk? Okay. Now, if you think about like what's happening, especially in the context of property testing, all the mass lies in the middle root T layers. So you don't want to ever go into these regions because an adversary could fool you by just putting a bunch of zeros here and ones here in the caps. So you want to always only walk in the middle. This is really where all the action of the hypercube is happening. You never want to be over here because that's like a very tiny fraction of the mass. And so, for example, here's a function where it's all zeros below n over 2, d over 2 minus root t, and it's all ones above d over 2 plus root t. And the dictator is only in here, right? So in this case, if you walk too long, you're going to end up here. Or if you walk downwards too long, you end up here. So essentially, it says you can't really walk more than root t steps if you want to find a violation, right? Because you're only flipping coordinates up or down. So what this says is like, we're going to walk root t steps. What's the probability of finding a violation? Well, with half probability, you're going to start here. At every step, you've got a 1 over d chance of crossing that dimension. You're doing it root t times. So it's about 1 over root t. So you start at x. Remember, you're not querying anything in between. You're only querying the end. So it's only querying x and y. But you can only walk root t steps. And so this is sort of suggesting that 1 over root t is the bound, like, or rather root t is the bound. And indeed, the root t lower bound is exactly this. It just says that suppose your function was one dictator, and you don't know which one. In each query, you can only walk root t steps. So you can only sort of effectively query root t coordinates for guessing the dictator. Okay? And so there is this directed isoperimetric thing, this Poincare inequality, and we know that it's tight. And it seems that the only way to get out of it is to have longer walks. And so, another bad pun. So basically, the route to root t is taking a longer route. I'll let you parse all the different routes. Okay. Question is, how do you analyze this path tester? So you need some structural insight on sets that are far from monotone. And the question is, really, how do you escape some set that is far from monotone? So this is, again, like connecting to lots of things in like, Markov chains and generally random walks, which is this issue of like, you don't want bottlenecks in your graph. And this is some kind of a directed bottleneck. So this is starting to suggest that the analysis of this is going to require some information about the conductance or the bottlenecks in this graph. And that's where, again, the connection to these isoperimetries comes in. Okay, so directed isoperimetric theorems. As we saw, the Poincare inequality says the influence is omega of the variance. And the directed version says inf plus, the directed influence is omega of the distance to monotonicity. So distance to monotonicity takes the place of variance. And you get a D query tester. I'm ignoring the epsilons here. So then what we discovered was that there is an inequality of Margulis. I'll explain what this is eventually. It says inf times gamma of f is omega variance squared. And what we can do is basically like put a plus. We can direct all of these boundaries and we replace the variance with the distance to monotonicity. And this leads to a d to the 5/6 if you tighten the analysis. And sort of the culmination is there's this bound of Talleyrand, which is this incredibly scary looking expression, which is the expectation of the square root of the influence. I don't know. I don't know how we discovered that. Or actually, I have some idea, but you can ask me later. And this says this is omega the variance. And what Kottminzer and Safra did was essentially take that, put a plus over there and replace this with the distance to monotonicity. And that leads to the root t bound. So the point is there's this parallel between these classic results in sort of, I guess, essentially pure math. And you can kind of direct them. And once you direct them, there's a way of analyzing them to get testers. And so this is what happens for the hypercube. And it also happens for the hypergrid. Yes? Well, that would just be like, start from a 1 and get to a 0. And that you can analyze and yeah. Yeah. I mean, I guess that's just sort of like, that's just the normal analysis of a random walk on a hypercube. And there you can analyze it. You can take a long random walk and you'll exit the set. So here, it's kind of constrained because you can't take a walk that's too long because of direction. So this is a good point. So the point is, directed random walks are really nasty objects. Because if you think about it, there's no stationary distribution. If you walk long enough, you just end up at the top point. So you kind of have to analyze it at this intermediate length. And that's annoying because there's no notion of convergence. And that kind of throws everything off. The other thing I'll mention is that this inequality here implies everything else. So from here, you apply Cauchy-Schwarz, you can get here. From here, there's an easy way of getting here. And all of these bounds imply these bounds. So like this is like the master bound. Okay, any questions? Okay, so the plan now is I'm going to tell you what all of this really means. And it's really a question of how do you measure the boundary? And all of these are different measures of boundary, more and more complex, all saying that the boundary is at least the volume in various different ways. Seemingly, Talleyrand looked at this and this didn't make sense to him. And so he came up with this. That apparently is the story, that he didn't understand what this actually meant. And so he came up with this expression here. Okay, how do you measure the boundary? So now let's think of it somewhat graph theoretically. The boundary is really just a bipartite graph, right? Again, we're just doing with the hypercube. The greens are the ones and the blues are the zeros, right? So you have this part of the boundary where it's going from green to blue, and you have this part of the boundary where it's going from blue to green. And if you take a directed boundary, what you're just saying is you're only focusing on the part where the ones are going to zeros. So this is sort of G plus, this is really all the violating edges. And this, of course, are the non-violating edges. And so immediately now you can define sort of the influence graph theoretically. Again, equivalently, I can say the influence plus of x, the directed influence of an x is the out degree in the directed graph. So I'm only counting it on the ones. If I were to count on the zeros, I have to count in degree. Right? But it's basically the same thing. So the expected influence of a point in the ones is, again, just the total number of these directed influential edges divided by 2 to the d, which is the directed influence. And just sort of slicing the pizza a different way. It's the same thing. And if you remove the plus, then you're considering everything. And then that's just the standard notion of influence, right? So this is basically the edge boundary. So as I said, like if you look at the sort of anti-dictator case, this bound is tight, the influence is O of 1. So let's just say you're trying to understand this parameter. What are the classic Boolean functions that you would look on? You look at a dictator and you look at majority, right? And you say, what happens in majority? I planted it, So in majority, I'm taking anti-majority, like I'm taking ones below and zeros above. The influence is much higher. So what is the influence? It's actually root t. So why is it root t? That middle layer is like a 1 over root t fraction, right? That's like d choose d over 2. And each of those points is influence d over 2. Directed or undirected influence in this case doesn't matter. So you multiply the d over 2 times that, and you get this root t. So this is an example where it's small. This is an example for a monotone function. This is the highest possible. Now, you can also look at the vertex boundary, which seems like an equally useful thing to look at. And so what is the vertex boundary? Again, the picture tells you what's going on. If you want a formal description, it's just saying you look at all the x's, which have a value of 1, which is incident to at least one influential edge. So you're counting, formally, you're saying the indicator of the influence being greater than 0 and the expectation of that. Right? So this is the fraction of things that participate in the boundary. Now you're going to see something that is very fascinating here. Let me look at both the edge boundary and the vertex boundary of these extreme cases. So in the dictator, the edge boundary, again, that's theta of 1, right? That's the influence. The vertex boundary is also theta of 1 because everything is in the vertex boundary. In this majority or anti-majority case, the edge boundary is theta of root t, but the vertex boundary is theta of 1 over root t. It's just small. You see that over here, the edge boundary is the smallest possible value given Poincare, right? This is like the minimum expansion for that size. And here, this is small. Indeed, the edge boundary here is the lowest possible. That's the Poincare inequality. Over here, this is the lowest possible by Harper's isoperimetric theorem. So Harper's isoperimetric theorem says, if you take a subset of the hypercube, let's say half the elements, and you look at the size of the vertex boundary, it's at least 1 over root t. Indeed, it's the Hamming balls that sort of are the worst case, right? So you have this interesting flip where in one case, the edge boundary is small, but the vertex boundary is large. In the other case, the vertex boundary is small, but the edge boundary is large. And lo and behold, Margulis proves that actually the product is at least the variance squared. So what he says is that both of them cannot simultaneously be small in the hypercube. Now, there's an amazing fact, right? You cannot simultaneously get the vertex boundary and the edge boundary to be their minimum values. If you make one small, the other has to go up. I don't know how we saw that. The proof of this is not that difficult once you figure out the right inductive hypothesis. But the genius is in figuring out that this fact is actually true. Yeah? And so just to show you these examples again, remember this edge boundary is 1, vertex boundary is 1, so the product is 1. Edge boundary is root t, vertex boundary is 1 over root t, product is 1. And this holds for any function, any Boolean function. And so what we proved is a directed version of that, saying that even if you direct it, you can replace that with the distance to monotonicity. Okay? I didn't see any wows in the audience, but hopefully you've, not this. I mean, this, of course, we just followed what Margulis did, but Margulis to see that that was actually the thing. And why is this relevant for monotonicity testing? Let me give you a little hint. Well, we studied this example. We said, oh yeah, it's 1 over root t. Then we thought, look, by directed Margulis, if the influence, this sort of inf plus is O of 1, then a constant fraction of vertices lie on the directed boundary, and maybe you can pull off an analysis like this, even when just the directed influence is O of 1. So that was sort of where we were going. But then Talleyrand had this theorem where he defines this incredibly scary looking expression. If this is obvious to you, then okay. But for me, I looked at this and I said, I don't know what the hell this means, right? And he says, this implies Margulis by Cauchy-Schwarz. It implies everything. And you're scratching your head at this and you're like, okay, in expectation of the square root, like why? And what Kottminzer and Safra do, so I'll explain, is Kottminzer and Safra do is essentially prove a directed version of this statement, which is just saying inf plus, and again, you get like this distance to monotonicity, and they define this tal plus. So I'm going to unpack this for you, I promise. But before I unpack this, I'm going to make things even more complicated. Because if you read Kottminzer and Safra, they prove this, but then they say, actually, no, we prove something even stronger. This is their statement. They say for any edge bicoloring, they define this crazy objective here. Again, you don't need to understand this because I'll explain it in the next slide. But what they're saying is the min over all edge colorings of the expectation over x of the square root. And you're like, what on earth is this? So you sit down and you try to understand what's going on. So I'm going to give you the exact definition of this. This is called robustness. But then I'm going to tell you what it implies. And the implication will actually be something very easy to understand. By the way, I should say that this KMS, they lost a log factor here. And then there was a result of Pallavu, Raskolnikova, and Weingarten who removed that log factor. So what is the meaning of robustness? So you want some measure of, Talleyrand says this is a measure of surface area. And so the way he imagines it is saying, okay, so there's some bipartite graph here. I'm giving you a simple example. Think of a bipartite graph where 2 to the d, roughly 2 to the d vertices and 2 to the d edges, except these edges have this sort of funny behavior. The ones here connect to many zeros, and many ones here connect to the same zero. And at most, d of these could be connected, like this is the degree. So if you define the Talleyrand objective with respect to the ones, so the degrees here are like d, 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 then 1, 1, 1, 1, 1. So for about half the words, for many of the vertices, it's basically 1. So you basically get the Talleyrand objective as 1. You could try to define the Talleyrand objective with respect to the zeros, and you would effectively get the same thing. But you'll notice that different things are contributing. Like so in this part, the zeros, this is contributing, and here it's. But what Kottmanzer and Safra said is, this is actually in some sense a small boundary. Because sort of if you remove this and remove this, you kind of delete the whole boundary. So what they had is this weird notion of an adversary that assigns each edge to 0 and 1 to minimize the surface area. So think of it, each edge is going to be assigned either to the 1 or to the 0, and you only count the degree that is assigned. And the adversary does this to sort of minimize that Talleyrand objective. It's a little crazy, but essentially, imagine that this inf of the coloring says that for each x, you look at how many edges of the boundary got assigned to you and only take the square root of that. And if you follow the math over here, there's a way of assigning these edges. You assign these edges to the ones and you assign these edges to the zeros, and you can actually get this quantity to be much smaller. So my point is, what they're saying is even this quantity is large, hence this cannot happen. To unpack, especially towards the end of the day. But if you got lost there, don't worry. What they prove is this strange inequality, which they call the robust Talleyrand inequality. But what it means is something that is really amazing. And this, I promise you will understand. So let's just assume the distance to monotonicity is omega 1. So there's this bizarro objective that they say is at least 1. So what do we know? By directed Margulis, we know that the edge boundary times the vertex boundary is omega 1. We also know that the edge boundary is omega 1. So roughly what this means is there exists some r greater than 1, ignoring constants. So the influence is r, and this vertex boundary is 1 over r, right? Because the product is 1. So there's some r for which this is true, this r greater than 1. So what this says is, in your boundary, there exists some r, so that the number of vertices is 2 to the d divided by r, and the number of edges is r times 2 to the d. So what Margulis basically implies is that the boundary looks like this, or at least contains this. Now, suppose this was a regular graph at the boundary. There's absolutely no reason why that should happen. But suppose it was. Then what is it going to look like? You're saying there exists some r, so that the number of vertices is 2 to the d divided by r, and all the degrees are r squared. Why r squared? Because you're dividing r times 2 to the d by this, so you get r squared, right? So this is what would happen if the boundary was regular. The robust Talleyrand theorem of KMS implies that's what happens. Up to some loss of factors. That is absolutely insane. It says that the boundary essentially contains like a regular subgraph with these parameters. Okay, so this is, I'll sort of state it a little bit more formally. It basically says, you look at this directed boundary, you look at the graph that you get from there, there exists some r, so that the boundary contains a regular subgraph where there are 2 to the d divided by r vertices, and all the degrees are r squared. That's really what the directed Talagrand theorem, the robust directed Talagrand theorem says. This is up to some d to the little over 1 factor. So I'm hiding some small factors. But that is what the theorem implies. Which that, I mean, I don't know, it's just completely incredible that should be true. It's easy to see this is true for like the majority or like very well-structured functions. But this is true for any function. For any function, the boundary contains a regular bipartite graph with these parameters. I don't know how the hell they came up with that. Like this, like, yeah, anyway. So this is what, and so once you have such regular structured properties of the boundary, then the analyses of the testers become possible. So I have what, 10 minutes left, basically. So let me take maybe just 5 minutes to tell you a little bit about why this implies something for monotonicity testing, and then I'll just wrap up with some open questions. So again, just to be clear, I said the boundary size is 2 to the d divided by r, and degrees are r squared. There always exists an r for which this happens. So in the dictator case, the r is equal to 1. In the majority case, the r is equal to root t, right? And even if you took a majority of a subset of coordinates, then the r would be that subset. This is true for any Boolean function. Any Boolean function. Okay. So like, okay, whatever. Like what about monotonicity testing? And so, you know, I don't have much time left. So, well, what the hell? Let's see how far I get here. Let me tell you a little bit about how you can use that statement to analyze the monotonicity tester. So essentially, what they say is, let's say a walk is L persistent if you take an L length walk and you kind of stay in the same region. So from here, you took an L length walk and you started at a 0 and stayed at the zeros. And here you started at the 1s and basically stayed in the 1s. So this is what is called an L persistent vertex. So what is the probability that a single step changes the value? Just by sort of guessing and averaging, it's the influence divided by d. What is the probability that L steps changes the value? So it was at most L times that. Just like simple union bound. By Markov, you can argue that the fraction of non-persistent, the vertices that are not persistent is at most O of this quantity. Like if this is really small. So what you get is that the fraction of non-L persistent vertices is L times the influence by d. And I'm going to spare you some work, but essentially doing some extra work, you can show that this is essentially L by root t. So there's so for every L, you can kind of figure out what fraction of vertices are not persistent. And so what they do is, what Kottmanzer and Safra do, their analysis is you choose this length so that that fraction of non-persistent vertices is much smaller than your boundary. And so there's some portion of the boundary that is not persistent. And because this is a regular graph, if you remove a small fraction of vertices, you cannot damage the boundary too much. So the boundary is basically going to be all persistent vertices, which means that if you start here, you'll stay here. And if you start here, you would stay here. So all you need to do is to somehow cross this, and then you will stay here. Because these are all persistent. And then you have this really nice structure, which is the number of vertices is 2 to the d divided by r. All the degrees are r squared. So then you kind of do some relatively simple calculations. Sorry, I will. And you can show that the probability is 1 over root t. So I don't have time to show you this, but believe me that this part is actually quite easy. It's just some fairly straightforward combinatorics. It would be kind of the obvious thing. Like you basically calculate some probability, you add it up over a bunch of things. The magic is in the fact that you get the sort of property of the boundary, which has these things. And that's where all the monotonicity testing stuff happens. So essentially, what we can do is we can generalize a lot of those concepts to the hypergrid. It's sort of too much to cover over the next few minutes, so I'm going to skip over. I'm just going to sort of tell you that one can get a version of the Talleyrand theorem for hypergrids and proving that one can get some sort of root T for hypergrids. But I'm going to skip over that and sort of go mostly, let me sort of jump here. And let me instead give you the big question that remains, is what is the adaptive complexity of monotonicity testing for hypercubes and hypergrids? So we have this root T bound that sort of matches upper and lower bounds. And there's a beautiful result of Blaise and Belov's that shows that there is a d to the 1/4 lower bound. Chen, Weingarten, and Chia improved that to d to the 1/3. And every example here has a matching adaptive upper bound. So it's not clear what the answer is. What Deeparnath and I showed a while back is that there are actually, if you use adaptivity, you can get O of the influence of the function. So this proves an adaptivity gap for certain families. So it shows that there are certain families of functions for monotonicity testing where adaptivity actually buys you something. And so the big question is, what is the adaptive complexity of monotonicity testing? Is it still just root T, or can you actually go all the way down to here? And depending on the day of time you ask me, I'll give you a different answer. Right. More on directed isoperimetry. So Black, Kalemai, and Raskolnikova have this nice extension where they can extend the directed Talleyrand inequality for real ranges. And I think that will also hold for hypergrids. Renato Pinto over here has like a series of new works where he's basically, actually I should have said continuous functions. He defines variants of monotonicity testing for continuous functions and then defines all these directed isoperimetric inequalities in that continuous sense. So those are for continuous Lipschitz bounded functions. So it's sort of, you can see the analogs, but it's not clear which implies which. And finding the connections between his results and the discrete results, I think, is a super interesting, research direction. Kanon, Chen, Levy, Kamath, and Weingarten have an application of this robustness concept for distribution testing. And Yuichi Yoshida has been recently he told me he's doing like some kind of directed isoperimetry for general posets, like trying to apply these concepts for general posets. So there's a lot of interesting work to be done here. I think an immediate, I would argue, low-hanging fruit, potentially, is there's a result of Pallavu, Raskolnikova, and Weingarten who show that you can do this tolerant testing. You can estimate the distance to monotonicity with a root T approximation in polynomial time for the hypercube. I think we can also get that for hypergrids now, because it seems like we have the tools that we need. But I think I say it's low-hanging because I think that we have the tools that we need, but I don't think it's obvious by any means. And then there's also a result of Berman, Raskolnikova, and Yaroslavtsev on LP testing. And I think Sophia can comment more and see whether some of these techniques can actually get results over there. And so right now it's 5 o'clock, so I will end over here. Thank you very much.
Thank you. Is there any question for Sesh to conclude the day?
Yes. No. Can you just say a few more words about your adaptive tester?
Oh, the influence one? Yes. Yeah. So what it does is it's actually quite simple. It will do a long undirected random walk and then does binary search there to try to find a violation.
How long?
So the length of the walk depends on the influence. So it does something like d divided by the influence of the function. So the influence is low, it can afford to basically walk a lot, but it does an undirected walk. Yeah, but just to complete the analysis of the tester requires the directed isoperimetric bound of KMS. So you have to use these isoperimetric theorems to analyze it.
So I've got another question. Do we have any natural family of functions for which testing has a gap, but like such a weird gap as square root n versus n to the 1/3 or something like this?
So if you look at functions of constant influence, you can show that in the one-sided case, there's a non-adaptive root T lower bound. But our tester, which runs an O of influence, runs in constant time for that family of functions. Does that answer your question?
No, I meant like, no. So if we're hoping for n to the 1/3 upper bound for adaptive monotonicity testing, that would be like, oh, you get some saving, but like polynomial with like a, it's not an exponential saving. It's not like.
I see. Yeah. So I don't know if I'm answering your question properly, but if you look at the family that gives the d to the 1/3 lower bound, like for that already, there's that gap. Like you cannot. I mean, there's a matching adaptive d to the 1/3 bound for that family. So I'll just say that, like, the issue is for non-adaptivity, in the end, there's not much a tester can do if it's being one-sided, right? It's going to start at a point and query something that's above it. There's not much. If you look at these adaptive testers that are there specifically crafted for those families, they're insane algorithms, right? They'll compute the influence on a few bits and then try to collect them together, extract information about something else. So there's a lot more that an algorithm can do.
I think there is an exponential separation from weighted.
No, there are exponential separations. Maybe we should stop, but I was just wondering, like, it's not a very impressive gap if it happens.
Yeah, okay, I see what you mean. Yeah. Depends on who you're talking to.
Thank you. Is there any other question? Let's thanks Sesh again, and thank you for attending the whole day. So good news, tomorrow is also going to be a very good day of talks. Bad news, it's